Okay, this is where we left off last time. We were looking at this program and talking about functions. And just to step back for a moment here, we have an exam on the 9th. That's Monday. Is that right? Monday? Okay. And we did some pretty extensive review for that in our last session. Mainly, we went through the unanswered problems that are on the bottom of this web page. And if you missed that presentation, then you can replay that using the videos here. So what I'd like to do today is just continue on with functions. But if you have any questions related to the exam or some of the earlier problems that we were working on, I'm happy to do that as well. So are there any suggestions or questions?
I just had a quick question on lab 3, exercise 3. Just like a little hint, is it using like modulo on that?
Factoring numbers, you'll need modulo, yeah.
Yeah, so is it kind of like the one from the prime numbers, detecting the prime numbers and answering them?
It's similar but different. See here, the problem here is that you're given a number, say 100, and you need to factor it into its prime factors. So the prime factors are 100. Of 100 are 2, 2, 5, and 5. So what you do is you start with 100, and you start pulling out factors. And you'll want to pull out prime factors. So you could factor 100 as 2 to 25. But 25 is not a prime factor, so you want 2, 2, 5, 5. So there turns out to be a pretty simple way to do this, and that is just start at 2, and then use whatever number you have, say n, and do mod 2. And if you get a 0, then you know that 2 is a prime factor. And then replace n by n divided by 2. So then n changes from 100 to 50. And then keep trying 2. So see, 100 factors into 2 2s. So you want to keep trying 2 until 2 doesn't go in anymore. So now that you have 50, you try to do 50 mod 2, you get 0. So you know that's an even. That's a divisor, so you take out another 2. So you do 50 divided by 2, you get 25. You try 2 again, 25 mod 2, that's 1. So that's not, you've taken out 2 2s, and you can't take out any more. But now you're left with 25. Then you try 3, 25 mod 3. And that's non-zero, so 3 is not a divisor of 25. Then you can, because you don't want a non-prime factor, so you don't want to try 4. On the other hand, so you could test to see, is 4 prime? No, then skip over it. You could do it like that, but the thing is, once you reach 4, you've already tried 4's factors. We've already pulled out as many 2's as we can. So we can go ahead and try 4 anyway, because we're never going to get it. 4 will never be an even divisor in this algorithm. So you just do 25 mod 4. It's non-zero. And go to the next number, 5. 25 mod 5 is 0, so you can take a 5 out. So you take n, which is now 25, divide by 5, and you're left with a 5. And then you can take another 5 out. And then you're left with a 1. When you finally reach 1, then you're at the end. So you've taken out 2 2s and 2 5s. That's it roughly in words how to solve that problem in a simple way. And there's other ways of doing it. Does that make sense? Anybody else? it's an interesting problem. And when you look at the code, it turns out to be pretty compact. It's not big. It's not a big program. It's a little program. And it's easier to use a while loop rather than a for loop. So try using a while loop. So you start with 2, try to take as many 2s out as you can. Once you've done that, go to 3, take out as many 3s as you can. You've done that, and so on. Actually, maybe you use a for loop and then a while loop within the for loop, something like that. You play with that, you get that to work. Any other questions? Yeah.
Number 4 on the exam practice, when we didn't.
Number 4?
Yeah.
The one with an answer or without an answer?
It's the one with the answer.
This one here?
Yeah.
When the code in figure 3 runs, what does it output to the console? Oh, there's figure 3 right there. So let's talk about this one. So there's 3 statements. And the tricky thing about this is this post increment. So that's an increment that's done after you use the variable in the expression within which it appears. So we start with n equaling 9. And here, just to make it simpler, I'm going to show you how to track the state of these variables. So we've got an n, we set it to 9. And that's it. So the first line is pretty straightforward. Now the second line, we're going to allocate or set aside or define a k, and then we're going to assign it the result of this expression here. So this expression, the last thing we do, well, not the last thing we do, but we'll need to evaluate what's in the parentheses before we evaluate that multiplication. And it's 1 plus n plus plus. So what do we do there? So we need to increment n. Do we add it to 1 and then increment it, or do we increment it and then add n to 1?
You have one first.
Yeah, add n to 1 and then increment. You're going to increment later. So n is 9, so if we add 1, we get 10. So this expression evaluates to 10. 10 times 2 is 20. Now we need to increment n. n becomes 10. See, so we assigned a k first, then increment 10. Increment n. And then in the next expression, we need to do what's in the parentheses first. But here we have the pre-increment, so plus plus k. So do we add k to n and then increment k? Or do we increment k and then add k to n? Increment k first, exactly. So let's go ahead and do that. We're going to increment k to 21. So k is now 21. We'll add it to n. So that becomes 31. And 31 mod 3 is 1, right? Because you can take out 10 3s and you're left with 1. I hope I put the right answer down for that. 1, got it. All right. Is that okay? Everyone get that? All right, let's go back and look at functions again. And reference parameters, I wanted to talk about this. Let's take, just kill this. Let's play with a number n here. We'll start with n equaling 0. And then we print n. Let's see if we got that. So we print n is 0. Now let's call the function, call it increment, just call it increment. And it takes an integer n. It's a pretty simple function. Just increments n. What do we print when we run this code? What do we print? We print 0 or we print 1? Now let me tell you that here, this is it's called pass by value. So the value of n, see this n here, is only visible inside of main. It's declared here, it's visible here, it's visible here, but it's not visible outside of main, it's not visible here, but because actually this is a different n. This n, it has the same name n, but it's the function argument or the function parameter n, which is different than the n that's in this other function. See, the functions are separate. The bodies of the functions don't look into each other. They're not aware of each other's variables. So this n and this n are the same thing. They represent the same storage area in memory. And this n and this n and this n, these three instances of n all represent the same thing, which is a different storage area. So we've got two n's going on in this program, naming two different things. It's like having two people in the classroom named David. You know, there's a David there and there's a David here. It's just the same name, but there's two different people. Here we have the same name, but they're two different variables. This is an equivalent program. That's an equivalent program. We just changed the name of the parameter, but that change has to be synchronized with, you know, the instance of that variable in the function. So this issue is called scope. So we say that k, the scope of k, is limited to the body of the function. Here, the scope of n is limited to the body of the function. Actually, n here, this will not compile, because when the compiler gets to this line and it says n, okay, but n is not defined, because we don't define it until here. So the compiler analyzes this in a linear manner. Let's check that. Let's see that. We'll say the compiler is going to say n is undefined. Use of undeclared identifier n. So we want to define the identifier n first, declare it, and then we can use it. Now look what happens. When we pass in n to increment, a copy of the value of n, which is 0 at the time we call increment, a copy of that value is copied into k. K is now 0. We increment K becomes 1. And then we return. And when we return from the function, we actually discard K. We don't need it. We're done. We're done with the function. So this function calls increment. When we call increment, it creates a copy, it increments a copy, and then it discards the copy. So n is unchanged, which n is still 0. We just print 0. Now what happens if we do this? Does that change anything? Does that change? Anybody know? Doesn't change anything.
No.
It's just the name. We're just happen to be using the same name. The same thing is happening. We're creating a copy. We're assigning it into a different variable. It happens to have the same name, but it's in a different scope. It's like there's a David in this room, and next door there's a David in that room. And I say David in here, I mean me. And I'd have to go into the other room to say David for the other David to acknowledge. So that's called scope. What's the area in which that name is valid or means the same thing? Now, if we did something like this, that's a conflict because we're defining two different variables, but we're giving them the same name and the same scope. So that will be rejected by the compiler. Redefinition of n. See? We can have a different n in a different scope, but we can't have a different n in the same scope. That's called redefinition. That's not allowed. But how can I want to increment n, though. I really want n to be incremented here. How do I do it in the function? What we do, instead of passing by value, instead of passing n by value, we pass by reference. We do this. We tell the compiler, don't make a copy of what's in the argument to the function. Use the variable that's sent into the function directly. Let's not operate on a copy of that argument. Let's operate on that variable as it exists in the calling code. So this is called a reference parameter. I put an ampersand here. This is a reference parameter. Now this n, all of a sudden, this n does not reference a separate variable anymore. It references the same variable that this n references, which was defined here. So when we do plus plus n here, we're operating on that variable that was created inside main. So this will print 1, because now we're modifying that variable in the calling code rather than a copy of that value from that variable. Now it's 1. What happens if I did this? Do we get a different behavior? No, it's the same thing. It's saying, we're telling the compiler, let k refer to, because of the ampersand, let k refer to the variable that was passed into the calling function. Don't make a copy of its value. Let's reference it directly. So we're going to operate on it directly. We're not going to operate on a copy. Now I've got two different names. Like some people call me David, some people call me Dr. Turner. I got two different names, but I'm the same person. So that's the business with reference parameters. That turns out to be extremely important You have to think about this all the time. And it's not just this language, it's all the languages. You have to think about whether a copy is made of an argument, of a variable, or whether you're working on, whether you have obtained a reference and you're operating on that entity that was passed to you from some calling code. And then we talked about scope as well. And then there's this idea of stepwise refinement, which I also call incremental development. And I have been talking about that already. We'll continue to look at that. And pseudocode, that means not writing the code itself directly. It's writing, like in comments, some description of what you want the code to do. Something that looks almost like code, but it's not code yet. So you use that in your planning stages of your problem-solving process, and then you end up transforming pseudocode into regular code. And what I've been doing is sometimes I'll put pseudocode in a comment, and I'll implement what's in the comment, and that's another way to do it. Understand code by performing walkthroughs. That's what we've been doing a lot already. Analyzing the code. In the last problem we looked at with the post increment, the pre increment, the way I kept a record of variables and their states as we executed the code mentally. That's a walkthrough. And here is understand the concept of a precondition. So we could have a precondition like, let's say, divide by. We have this function, and we're just simply going to divide x by y and return that value. I'll just call it divide. Divide 1 by 2. See how that works? So divide, and this has to return a value. We need to specify the type of the value that the function returns. The function returns a double, a floating point number, an 8-byte representation of a floating point number. It's a double precision floating point number. So we take the first argument and divide by the second argument and return the result. So 1 divided by 2 is 0.5. Let's see that work. Well, what if we tried this? 1 divided by 0. I don't know what it's going to do. Oh, infinity. So we don't want to allow the function to be called with the divisor being 0. So we can use an assert statement in there. We can assert that y is not 0. Oops. We need to include the header for assert, which is C assert. Now we have an assertion failure. That's one way to do it. So that y is not 0 is called a precondition for this function. And you can use insert statements to enforce preconditions. In this class, we're going to use assert statements to express tests, automated tests. But you can also use them as preconditions too. Or anywhere in your code that you want to check your logic. It's good to put an assert. And so also understanding how to test programs, including the concepts of unit testing, boundary cases, and test coverage. So unit testing is to test a piece of your program. Normally you test a function, so that's called a unit. So let's test this function, let's test another function. And then all the functions, all the units have been individually tested. Now we'll just do an integrated test where we pass in data and check to see that all the functions are working together correctly. And then boundary cases, that's where oddball values are passed in. Like if your function takes an integer, well, you better try 0. You should try negative value, -1, so on. So you try these boundary cases. So the purpose of a test is try to make the program crash. And if you can't succeed, that means you've got a correct implementation, or hopefully a correct implementation. If you don't try hard to find a value or set of values that crashes your program, then you haven't thoroughly tested your code, and so it might still contain bugs. So that's called test coverage. We want to make sure that as much of the code is tested as possible. Normally in code you have branches, like where you have if statements. And if some condition is true, then do this, else do something else. So you want to have a set of tests in which all branches of logic are executed. That's called good coverage. So coverage. That's the concept of coverage. And we'll be talking about this a lot as we go on, especially now that we're talking about functions. You'll have exercises in which you need to write test code. And your test code needs to have good coverage, needs to test the boundary cases, the oddball values, as well as normal values. And that's that. How to use a debugger to find logic errors. Now, I'm not presenting on how to use an integrated development environment on IDE, it's called, like Visual Studio or Xcode. I can do that if there's an interest in here for me to present on that. But in those IDEs, typically you use something called a debugger where you set breakpoints and you can halt the execution of your program and examine the state of the variables in your code. And you use that to troubleshoot bugs that are in your code. So I could at some point demonstrate that, but I'd have to show you like Visual Studio or Xcode. There's a way to do it using the command line, but it's too messy and complicated. I can't remember how to do it. It's very impractical. But in a visual interface like Visual Studio, it's very easy to use the debugger. And normally, when you write programs, you work in a visual interface like Visual Studio or Xcode. That would be the typical environment that you use to write code, especially C++. And so this topic I probably won't cover. All right, let's start a new problem here. Well, before I do that, has anybody looked at these? And any questions about these problems? Lab 4. All right. All right, so let's solve. I thought of a problem I wanted to work on this morning. I was just trying to think, how can I illustrate functions? And I came up with a problem that I think is really interesting, and we have enough time to do it. So let's suppose we have a game show on television, and there was a show, I forgot what it was called, like you have three doors or 3 curtains, and the contestant picks one of the curtains. You know, the two of the curtains have some goofy prize, like a goat or something, and then the other curtain has a brand new car. Right? So you want to pick the curtain with the car. And so you have a choice, one of three doors. And the guy that did this show, his name is Monty. I think Monty Hall, maybe. Does anyone know this? Is that right?
Let's make a deal.
Let's make a deal. That's it. Yeah. So let's implement that show. Okay. Let's see how it goes. Let's implement that show. And what we're going to do is this. We have three doors, and we'll have a prize door. And when the program runs, we'll randomly pick a prize door. So the doors are numbered 0, 1, and 2. 0, 1, and 2. Or if we want to number the doors, let's do it differently. Let's number the doors 1, 2, and 3. So how do we do that? How do I randomly pick from the numbers 1, 2, and 3?
Add a 1.
Just add 1. That's it. Thank you. So the prize door is a random door from the following set. And let's just see how this works. Two. Oh, we're always getting 2. What's the problem?
Random number generator.
Exactly, and I totally forgot actually. We need to seed the random number generator. We'll seed it with number of seconds from some epoch, and I don't need to include anything, but you might to get that. Two, 3. There we go. 1, 2, 3, 3. So 1, 2, or 3. Looks good. Look at that. It was so simple. I thought, oh, it's silly. I'm gonna go ahead and test this anyway. And it turns out we had a bug, right? We didn't seed the random number generator. So it's just, this is an incremental development, or it's a form of stepwise refinement, I think, roughly equivalent to that. So now, instead of just printing the prize door, let's ask the contestant to to pick a door. And the door number is I'll call it the pick. Well, the pick door. We declare it and then use cin and read into the pick door. Then if the pick door equals the prize door, you win. Else, you lose. You actually win something, but it's something silly, like I think I remember a goat.
You forgot the opening.
I forgot the opening quote. Thank you. Excellent. That saves us some time. So how often should we win?
1/3.
1/3. There we go. 1/3 of the time we should win. Pick a door. 1. you win. Pick a door, 1, you win. Pick a door, 1, you lose. Pick a door, 1, you lose. You win. I'm winning a lot, but, you know, not a huge amount, but I'm. 1, 2, 3, 4. 1, 2, 3, 4. Is that winning 50% of the time? That doesn't sound right, does it? Let's check this one. Let's run it 6 times. Let's see if we win 3 times. We won it once. So we won it once. We won it once out of 3 times, so that's a third. And we won once out of 5 times. Once out of 6 times. So we did well the first time we did it. And we didn't do that well the second time. I guess it's random, so it's want to be exactly 1/3, but in the long run it'll be a third.
Why do you add 1?
We add 1 because, you know, this is a contestant, and the contestant's going to say door 1, 2, or 3.
Okay.
But when we use the random number generator here, we're going to get a value that starts at 0.
Start off.
So from 0, 1, and 2, we want to add 1 to transform 0, 1, and 2 to 1, 2, and 3.
Got it.
Now, what happened in the show is Monty does this clever thing. He goes, you know, you pick a door, right? And I say, I like door 1. And he goes, all right. And he goes, let's look at door 2. And then he goes, would you like to change your choice? You want to stick with door 1, or do you want to change it? You can change it to door 3 if you like. What would you do?
Stick with it.
Stick with it. What's the probability if you stick with it?
66%.
How many people would change the door? How many people would stick with door 1? Let's investigate that. So we need to add some logic here. We have the pick door. So we're going to reveal a door. So there's 2 cases here. Let's suppose the pick door is the prize door. You know, this is a little... It's hard to do this right, but I'm going to try. So if the pick door, so what we're trying to do is implement that case where Monty reveals a door that we didn't pick, but that door can't have the prize in it, okay? So how do we do that? So if maybe we can, let me see if I can use functions for that. Let me think for a second. Should we use a function for this? Let's do that. So we want to reveal the door. Did I spell reveal right? That's okay. Reveal the door. You know what? I'm not going to do it with functions. It's too hard. Let's do it right here for now. So if the pick door is the prize door, then let's reveal a door. If the pick door is 1, then we're going to reveal door 2 or 3. So let's start just by revealing door 2. So door 2 is revealed. Else, if the picked door is not door 1, I'll do it like this. If the picked door, I'll do it like this. If the picked door is 2, then we'll reveal, say, door 1. If the picked door is 3, which it has to be, then we'll reveal, say, door 2. So that's if the picked door is the prize door. And this is the case where the picked door is not the prize door. I don't want to lose people here. Let's see. I'm just going to say, I'll just do this. If the picked door is the prize door, where was the problem there?
Don't you have to use else if for the other two conditions?
Oh yeah, that's right. Thank you. Thank you very much. That's else if. Pick a door. We didn't pick the prize door. We picked the prize door and that system revealed door 2. We picked the prize door and the system revealed door 2. Same thing, we keep getting 1. We didn't pick the prize door, okay. So, actually, in this case, when we pick the prize door, we really should randomly select between the other 2 doors. Maybe we can do let's do a function to do that. We're going to reveal a door, and we're going to pass in, door 1 and door 2. We're going to pass in 2 doors. And then we're going to randomly pick a door to reveal. There we go. Because we don't want, we want to, if the pick door and the prize door are 1, we don't want to just say door 2. We want to randomly select between 2 and 3. So we're going to call reveal door 2 and 3. We want to randomly reveal a door between those 2 doors. And if the pick door and the prize door are both 2, then we want to randomly reveal between 1 and 3. If the pick door and the prize door is door 3, we want to randomly reveal among the doors 1 and 2. All right, that's it. So we're using a function for that. Let's see how that works. Up. So we got it that time. First time we didn't pick the prize door. Second time, our door 1 selection was the prize door. And we ended up calling that function to randomly pick door to reveal. So this, once again, is an example of iterative development. How do we randomly pick between door 1 and door 2? Well, we use the rand function. And mod 2. Rand mod 2 gives a 0 or a 1. So if we get a 0, we'll do door 1 does not have the prize. Else door 2 does not have the prize. Whoops. Pick a door. Door 3 does not have the prize. We are really unlucky here. Door 2 does not have the. So now when our choice of 1 picks the prize, the door with the prize in it, we randomly select between doors 2 and 3. And that should work as well for the other doors. So 2 should do the same thing. It's hard to pick it. Only 1 out of 3 times we pick the prize door. Anyway, so it shows it there. So when we pick door 2 and it's the prize door, we'll randomly pick between 1 and 3. We can simplify this code a little bit. Take out some redundancy. I'll show that to you because this, we always print exactly this. So we can see out door. And then we can print door 1 here. And then, or print door 2. And then Then we tack on that. Do you see how that's a simplification there? Also, door 1 and door 2, I think is confusing. I'm going to do door A and door B so that we don't get confused with our numbering scheme, because we don't know what door A and door B are. Let's just check that test. Oops. All right, actually that didn't test it. There we go, that's not right. So that's good. There's many ways of redoing this to make it fancy looking. I think that's the simplest. All right, so we've handled the case when the picked door is the prize door, but what about the case where the picked door is not the prize door? We also want to call, we want to reveal one of the other two doors, but not, we want to reveal the door that is doesn't have the prize. Oh, there we go. So we know that the picked door does not have the prize in it. And so we don't want to reveal the door with the prize in it. We want to reveal the door without the prize. So we're forced to find that one. So we have to find that one. So if the picked door is 1, let's do it like this. If the picked door is 1, then if the prize door is 2, then we want to say, then we want to reveal door 2. Or sorry, reveal door 3. Else, reveal door 2. Does that make sense? So the picked door is not the prize door. We checked it already. The picked door is not the prize door here. So if the picked door, which is not the prize door, is 1, and the prize door is 2, then we'll reveal door 3. Otherwise, we'll reveal door 2. Else, if the picked door is 2, and then we do something similar. If the picked door is 2 and the prize door is 1, reveal door 3. Otherwise, reveal door 1. Otherwise, this is the case where the picked door is 3. If the prize door is 1, we'll reveal door 2. Otherwise, we reveal door 1. Sorry. That's right. Now we need to implement reveal door. Oh, we already have reveal door. Reveal, I don't like the name now, so reveal I'm going to call that reveal random door. Oops. Undo. We'll change the name of the function to give it a better meaning based on the code, the logic as we're evolving it. So we have reveal door. Let's see. Let's define a function reveal door, and we just take a single door. There it is. Let's see how it goes now. All right. Line 45, right here. I see the else needs to be preceded by a brace. It's line 40, what did I say? 43? 45. 45. There we go. Pick a door 1. Door 3 does not have the prize. Pick a door. Door 2. Door 3 does not have a prize. Door 1. So it should never, it should just give us a door that we haven't, that's not our door and it's not the prize door. That seems to be working. Now this logic here is, I think it could be simplified so it's easier to read. Let me try to do that. What do we do? Let's try this. If the picked door is the prize door, maybe this won't be easier to read. And the picked door is 1. No, I'm not going to do that. I'm not going to go down. I'm going to simplify these here. If the picked door is 1 and the prize door is 2, then reveal door 3. Does that look easier to look at? If the picked door is 1 and the prize door is 3, then reveal door 2. If the picked door is 2, 2, 3, 3, if the picked door is 2 and the prize door is 1, and this would be 3, then reveal door 3. If the picked door is 2 and the prize door is 3, reveal door 1. If the picked door is 3 and the prize door is 1, then reveal door 2. If the picked door is 3 and the prize door is 2, then reveal door 1. That's easier, isn't it? We have 2 cases, and I'm going to get rid of this quote. I'm going to get rid of that comment because the code is short enough to see what's going on. If the picked door is the prize door, and let's make it symmetric with the way this code looks here. if the picked door is 1, then reveal a random door between 2 and 3. If the picked door is 2, then reveal a random door among the set 1 and 3. If the picked door is 3, then pick from 1 and 2. Look at that. Does that make the logic easier to get? So what I'm doing here is, it started in such a messy state, but I'm always, kind of conscientiously cleaning the code and looking for opportunities to create more clarity in the logic. So it's easier to program, easier to maintain, easier to build the program. So this is called refactoring. So we're doing incremental development and refactoring at the same time. Let's see if that works. Pick door 1. Door 2 does not have the prize. Door 2. Door 3. So now after we reveal let's let the user reselect. So based on the door that was revealed, the user has a chance to pick a new door. We don't need to declare pick door again. So after we reveal a door, we're going to ask the user, which door do you want? You can change your mind. You can change your mind. Which door do you want? Pick a door. 3. Door 2 does not have the prize. Let's stay with door 3. You lose. Can someone keep track of this? So here's the strategy. You're going to stay, and we're going to change. So stay. So we just lost, right? We stayed and we lost. Pick a door. 1. Well, door 3 doesn't have the prize. We win. So we stayed and we won. Pick a door 2. Door 3 does not have the prize. Let's stay with door 2. We lose. I'm getting chalk on my keyboard here. Actually, let me show it on the... We only have a second here, but I think we can do it. And I'll do a new window. So this is the stay strategy. We have win and lose. So we have what, 2 loses and 1 win. Pick a door, 1. Door 2 doesn't have it, you lose. Pick a door, 2. 3 doesn't have the prize. Stay with the same door, we lose. Look at this. One more time. Pick a door, 3. Door 2 is not there. You lose again. Look at that. We are losing a lot. Now let's go with the change strategy. Do you think we're going to do any better? Pick a door, 1. Door 3 does not have the prize. Which door do you want? I'm going to change to door 2. You lose. Let's run it again. Pick a door, 2. Door 1 does not have the prize. Let's change to 3. Oh, you win. Pick a door, 2. Door 1 does not have the prize. Let's change to 3. We win. Pick a door, 3. Door 1 does not have the prize. We'll change to door 2. You lose. Pick a door, 1. Door 2, let's change to 3. You win. How many times did we go before? 6. 1 more to go. It's not enough.
You put it in the wrong row.
I did?
Yeah.
Oh, it's a win, right? Thank you. Thank you for that. All right, we picked door 2. Door 3 does not have a prize. Let's switch to door 1. We win. Look at the difference with the change strategy. Of course, we want to try more trials. You know, actually, the stay strategy, if you use the stay strategy, you're going to win 1/3 of the time you play the game. If you use the change strategy, you're going to win 2/3 of the time. Can you believe that? And most people pick the stay strategy. Now you know. Now you know the better strategy. Anyway, that's it. We're out of time. Quiz or exam on Monday.